Okay, dear students. So today we'll start our session. Okay, so today we will discuss about open channel flow as per GTU syllabus in 4th sem civil students. Subject is fluid mechanics and hydraulics. In that module number 6 is open channel flow. And today our topic is also introduction about open channel flow. Okay, so what is open channel flow first of all? So today in this particular session we will discuss some basic concept of mechanics as well as open channel flow. Okay, so as our topic is itself introduction about open channel flow, so first of all we have to understand what is open channel flow. Okay, so liquid flow with free surface at atmospheric pressure is called open channel flow. Okay, so this is a very simple definition. The liquid which flow with free surface at atmospheric pressure is called open channel flow. Open channel flow are flows with free surface that have many applications. Okay, you can find so many applications: rivers, streams, aqueducts, canals, sewers, irrigation, water channels. As are so many applications of the open channel flow. Sometimes in examiner can ask the comparison also between the pipe flow and open channel flow. So I have listed here some points. What is pipe flow and what is open channel flow? So in pipe flow you can see it flows with the solid boundary, whereas in case of open channel flow it is open with free surface. Okay, that's why you can say I have put one figure. Okay, you can say snapshot is there, not a figure, it is a snapshot of the open channel flow. You can find so many things. I have already given the example. Then second point, in pipe flow it is a fixed cross section, whereas in open channel flow it has a variable depth. Third point, in pipe flow it is driven by pressure gradients, whereas in the open channel flow it is driven by gravity force. Okay, flow is driven by gravity force. And in pipe flow, fourth point is it is mostly circular. Okay, we generally consider it is a circular pipe, whereas in open channel flow it is all kind of shape. Okay, you can see in example even river, stream, aqueducts, canals. So you can understand that it has so many shapes. Okay, so this is very general comparison of pipe flow and open channel flow. You can write in your own words also. Now further, open channel flow deal with the flow of water in open channels. Okay, and pressure is atmospheric at the water surface, and the pressure is equal to the depth of water at any section. Okay, so that is very important. Further, pressure head is the ratio of pressure and the specific weight of the water. Elevation head or datum head is the height of the section under consideration above datum. Okay, so right now we are discussing some concept of the open channel flow. Velocity head, as you know, it is v square by 2g, is due to the average velocity of flow in that vertical section. Okay, and the flow of water in an open channel is mainly due to the head gradient and gravity gradient. Okay, open channel are mainly used, we have already discussed, to transport the water for irrigation, industry and domestic water supply, irrigation supply, etc. Now there are some laws also. Conservation law. So in conservation law again there are three types of law: conservation of mass, conservation of momentum and conservation of energy. So what is conservation of mass? In any control volume consisting of the fluid, means water, under consideration, the net change of mass in the control volume due to inflow and outflow is always equal to the net rate change of mass in the control volume. This leads to the classical continuity equation balancing the inflow, outflow and storage change in the control volume. Since we are considering only water, which is treated as incompressible fluid, the density effect can be ignored here. Okay. Then next one is conservation of momentum. These laws state that the rate of change of momentum in the control volume is equal to the net force acting on the control volume. Since the water under consideration is moving, it is acted upon by external forces. And essentially this leads to the which law? Newton's second law of motion. Okay. And third one is conservation of energy. What is that? This law states that neither the energy can be created or destroyed. It only changes its form. So we have so many times discussed about the control volume. Okay, so I have listed here the definition of control volume. What is control volume? Control volume is a mathematical abstraction employed in the process of creating mathematical model of physical processes. Okay, and in an internal frame of reference, it is a volume fixed in a space or moving with constant velocity through which the fluid is flowing. Fluid generally we call as a gas or liquid. Fluid is not only water. Fluid meaning is it is gas or liquid. So this is the basic definition of control volume. So as we already discussed in conservation of mass, conservation of momentum, I use the word control volume. So this is the basic meaning of control volume. So, okay, so we are discussing about the conservation of energy. So, this law states that neither the energy can be created or destroyed, it only changes its form. Mainly in open channel, the energy will be in the form of potential energy and kinetic energy. Okay, and potential energy is due to the elevation of the water parcel, while the kinetic energy is due to the its movement, whisker by 2g, that we know. In the context of the open channel flow, the total energy due this factor between any two section is conserved. Okay, and this conservation of energy principle leads to the classical Bernoulli's equation. We know very well E upon rho plus V square by 2g plus z is equal to constant. Now come to the classification of open channel flow. Open channel flow are the characterized by the presence of a liquid gas interface called the free surface. Okay, it's called free surface. So there are two types: natural flow, you know, rivers, creeks, flood, etc., and human-made system, that is freshwater aqueducts, irrigation, sewer, drainage ditches, etc. Okay. Now you can see here I have just put one figure. Open channel flow, it is classified in steady and unsteady flow. This is with respect to time. Okay, and again it will be steady flow is classified in uniform and varied. Here it will be with respect to space, and varied flow again classified in this way: gradually varied flow and rapidly varied flow. I will show you. Okay, so first one is steady flow. So what is the steady flow? In steady flow, fluid parameters such as velocity, density, pressure, acceleration, etc. at a point do not change with time. This is very important word. I am showing with my cursor. This is very important. Okay, do not change with time means quantity of water flowing per unit time is constant. And if you want to define mathematically, you can define this way: del v means your velocity with respect to time. It will remain constant, means is equal to 0. Del v upon del t is equal to 0. Same way pressure. So del p upon del t is equal to 0. Okay. Okay, this is a del rho, this is del p upon del t, and here del a acceleration. This is the acceleration. Del a upon del t is equal to 0. So means velocity, density, pressure, acceleration, etc. at a point do not change with time. It is called steady flow. Steady flow. Now next one is unsteady flow. Here I have done mistake. It is not known unsteady flow. Okay. So please make a correction. This is unsteady flow. So in unsteady flow, fluid parameters such as velocity, density, pressure, acceleration, etc. at a point changes with time. Means it is not constant per unit time. It changes. So if I want to represent same thing with a mathematical representation, I can write this way: del v upon del t is not equal to 0. Okay. Same way del p upon del t is not equal to 0. Del a upon del t is not equal to 0. So it is called unsteady flow. Okay, unsteady, not non-steady flow, but unsteady flow. I have done here mistake, so just make it correction. Now uniform flow. Next definition is, so a flow is said to be uniform if the flow characteristics, that is depth, discharge, and average velocity, remain constant along the length of the channel, is called uniform flow. Means here we are talking that these all the parameters are remain constant with respect to space. Okay, so you can say del v upon del s is it is denoted space. So del v upon del s, again we have to consider time also. So t is equal to constant, but with respect to space is equal to 0. Same way, okay, so you can see here flow in open channel is also classified as uniform, non-uniform depending upon the depth. Okay, uniform flow encountered in long straight section where head loss due to friction is balanced by elevation drop, and depth in uniform flow is called normal depth. You can see in the figure. Okay, your water is flowing with a constant velocity. Okay, and your depth is also constant throughout the length of the channel with respect to space. So that is very important. Non-uniform flow, if flow is said to be non-uniform if the flow characteristics, that is depth, discharge and average velocity, does not remain constant along the length of the channel. It's called non-uniform flow. The same thing here, you can write del v upon del s respect to space by keeping time is constant. Okay, is not equal to 0. Means, what is the meaning? It is not same throughout the length of the channel. Okay, so that is non-uniform flow. So we have discussed steady flow, unsteady flow, uniform flow, non-uniform flow. The next one is gradually varied flow. A flow is said to be gradually varied whenever the depth changes gradually along the channel. Okay, so it is changes gradually, not a sudden drop. It's a gradually flow. Now, rapidly varied flow, whenever the flow depth changes rapidly along the channel, the flow is termed as the rapidly varied. Okay, abrupt changes is there, abrupt change in the depth is there, that is called rapidly varied flow. You can see I have put here one figure. So you can see obstruction cause the flow depth to vary. Rapidly varied flow, short form is RVF, occurs over a short distance near the obstacle, whereas the gradually varied flow GVF occurs over a larger distance and usually connects the uniform flow and rapidly varied flow. You can see the figure. This is your uniform flow, then this section is your gradually varied flow. Then you can see sudden changes in the depth. So this will be your RVF. Then again here you can find somewhat gradually varied flow, and then it finally connects to the uniform flow. So this way your flow is flowing. Okay, so this is very simple phenomena. So this is all about the uniform, non-uniform, gradually varied flow, rapidly varied flow. The next one is spatially varied flow. Whenever the depth of flow changes gradually due to change in the discharge, the flow is termed as a spatially varied flow. So one more term is that spatially varied flow. Okay. Now next one is laminar flow, turbulent flow and transitional flow. So what is the laminar flow? The highly ordered fluid motion characterized by the smooth layers of the fluid. The flow of high viscosity fluids such as oil at low velocity is typically laminar. Means here the flow particles, fluid particles are flowing in a one straight line. Okay, in a one straight, they are not crossing each other. They are flowing at a one straight path without crossing each other. That flow is called laminar flow. Means here velocity is very low. They are flowing at a very low velocity. So you can say it is a laminar flow. Okay. Turbulent flow, the highly disordered fluid motion that typically occurs at high velocity and is characterized by the velocity fluctuation. The flow of low viscosity fluids such as air at high velocity is typically turbulent. So if you want to understand here, it's a very simple. You can take any example. Suppose if you open the tape, okay, and water is flowing from that particular tape, okay. So initially you have keep your velocity very low. So water will flow at a constant rate. Means you can say in a one single path, okay, straight path. So you can take that example is laminar flow. But as you increase the velocity, that flow will water will flow randomly, okay, by crossing each other, fluid particle crossing each other. Means at high velocity that flow will become turbulent flow. Okay, so there are so many examples are available between laminar flow and turbulent flow. So in turbulent flow, fluid particles are not moving in a straight path. They are moving randomly and they are crossing each other. Okay, fluid particles are crossing each other. So this is the example of turbulent flow, laminar flow. And one more, that is a transitional flow, a flow that alternates between being laminar and turbulent. Means in between laminar and turbulent flow, the flow is called transition flow. So generally we have classified based on the Reynolds number this all the types of flow. If your Reynolds number is less than 2000, okay, we call generally laminar flow. If your Reynolds number is between 2000 to 4000, we generally call as transitional flow. And if your Reynolds number is more than 4000, we generally call this flow as a turbulent flow. Okay. Then depending on the Froude number, one more word is there. The flow in open channel classified as subcritical flow, supercritical flow, and critical flow. And Froude number can be defined as Fr is the Froude. Okay, R is suffix here. Fr is equal to V upon under root GD. There are so many types of number, dimensionless number we call as a Reynolds number, Froude number, Weber number, Euler number, Mach number. Okay, so this is one of the number, Froude number, that is a dimensionless number. So based on that, we have classified the open channel flow, that is the subcritical flow, supercritical flow, and critical flow. So if your Froude number is equal to 1, we call that flow is a critical flow. Okay, often a transitional flow. If your Fr is less than 1, is called subcritical flow, means a relatively deep, slow flow. And if your Fr is greater than 1, it is called supercritical flow, means relatively shallow or fast flow. Okay, so this is all nothing but significant value of Fr that you have to remember. These are some of the peaks of uniform flow. Okay, uniform open channel flow. You can, I think you can understand very well what I want to convey. So this is just only peaks are there. Now we will discuss some parameter of the open channel flow. Okay, because there are so many you can say cross sections are available, rectangular section, tabular section, circular sections. Okay, so these are then what is perimeter, okay, area, okay, hydraulic radius. So these are the parameters of the open channel. So before we discuss, there are some definitions that we have to understand. So I have listed here. First definition is depth of the flow, that is the y. We denote by y. You can take any nomenclature, but generally we denote by y. So it is nothing but vertical distance from the free surface to the bed of the channel is called depth of the flow. Whenever I will use the word depth of the flow, means this is the meaning, vertical distance from the free surface of the water to the bed of the channel. Okay. Second one is depth of the flow section. Here it is the depth of the flow and here it is depth of the flow section, we denote by D. It is depth of the flow normal to the channel bed. Normal is perpendicular to the channel bed. Then channel top width, that is denoted by T. It is the width of water surface exposed to the atmospheric pressure. Okay, so top width, channel top width is called nothing but width of the water surface. Okay, which is exposed to the atmospheric pressure. And next one is freeboard. Freeboard is the vertical distance from the top of the channel to the water surface. Okay, your water surface is there and above that your top of the channel is there. Okay, so top of the channel, distance from the top of the channel to the water surface. Top of the channel to the water surface. Top of the channel to the water surface is nothing but freeboard. And this free space is required to prevent overflowing of water due to waves and fluctuation. Okay, so what is freeboard? It is a distance between the top of the channel to the water surface. Okay, so generally we provide the freeboard, and freeboard is generally provided based on the discharge. Okay, the table is you can also find from the internet also for different discharge how much freeboard we have to provide, that value is given there. The next one is cross sectional area of the flow, that is A, is the area of flow through which flow takes place. Okay, and the cross section is taken as a vertical section axis. Okay, so this is not, it's very simple one. Then wetted perimeter, we generally denote by P. It is the length of the boundary in contact with the liquid flowing in cross section plane axis. So that is your wetted perimeter. Then what is hydraulic radius? R. It is the ratio of cross sectional area of the flow to the wetted perimeter. Means generally we denote by R is equal to A by P. Ratio of cross sectional area A divided by the wetted perimeter, that we have discussed. Then hydraulic depth D. It is the ratio of cross sectional area to the top width capital T. So you can see here it is previous one is hydraulic radius and this is the hydraulic depth. So don't confuse. So it is a hydraulic depth is the ratio of the cross sectional area to the top width T. Then bed slope, we generally denote by as O. It is the slope of the bed of the channel. Okay, slope of the bed of the channel. Hydraulic slope we denote by SF. It is the slope of energy line. Means if you want to define, it is the head loss due to friction in length L divided by total length. Then water surface slope. It is the slope of the water surface line at any section, and if the depth varies along the length, if the depth y varies along the length x of the channel, then dy by dx is the slope of the water surface line at this section. Okay. Now we can see weighted parameter P. The length of contact between liquid and sides and base of the channel is called weighted parameter. You can see in the figure. This is your weighted parameter. So length of contact between liquid and side and base of the channel. This is side and this is the base of the channel, is nothing but ultimately your weighted parameter. And we generally define by this way: P is equal to B. This is your okay, and this is your twice D on the both the side. Depth is there. So P is equal to B plus twice D, where D is the normal depth. You can see B and this is your depth. Hydraulic mean depth or hydraulic radius. If cross sectional area is A, then R is equal to A by P. I already told you hydraulic radius is nothing but R is equal to A by P. For rectangular channel, area is B by D and P is B plus twice D. That we have discussed. Now, empirical flow equation for estimating normal flow velocity. So there are some empirical equation. One of the empirical equation is Chase's formula, which is given by Chase in 1775. Can be derived from the basic principle, and it states that V is equal to C under root R into S. Okay, now I have put here one equation. Now here if I we have already discussed the parameters, okay, definitions. So now here it is easy to you to understand this meaning. Okay, what is Changes want to say us? Okay, so V is equal to C into under root R into S, where V is the velocity, R is your hydraulic radius. You know now very well that what is the R, and S is your slope of the channel. And what is C? C is the Chase's coefficient and is function of hydraulic radius and channel roughness. It depends on that. This C, Chase's constant. Okay, then next one is Manning's formula. After changing Chase's formula, Manning's formula. Manning's formula given by Manning's, okay, 1889. An empirical formula based on the analysis of various discharge data. And the formula is the most widely used. It is a very popular formula in fluid mechanics. So V is equal to 1 upon N, R is to 2 by 3 into S is to 1 half, where N is called the Manning roughness coefficient found in a textbook. Okay, and it is a function of vegetation. It depends on vegetation, growth, channel, irregularities, obstruction, shape and size of the channel. So I think I have listed here some. Okay, this is the Manning equation. V is equal to 1 upon N, R is to 2 by 3, S raised to 1 half. S is here, S is your channel slope in feet per meter or meter per meter. Okay, and in Manning roughness coefficient. More roughness in the channel will slow down the water, and smaller R will slow down the water. Okay, so this is just as per the equation. You can even take the judgment. Okay, if you take more value of N, means more roughness in the channel, will definitely slow down the water, and if you take the smaller R, means flow depth, will slow down the water. Okay, smaller slope will slow down the water, smaller slope will slow down the water. So these are some parameters that you have to understand. And here some of the, you can say, Manning roughness coefficient I have listed. For smooth concrete we generally take N is equal to 0.012. okay, for corrugated pipe we generally take N is equal to 0.025. For smooth soil N is equal to 0.03, and for cultivated soil N is equal to 0.04. okay, so just this is for your reference. Now channel hydraulic radius, R is equal to A by P. You know it is nothing but average flow depth, where A is the area of the flow cross section in square feet or square meter. P is the length of the line of the contact between the channel and the water on the area, means our weighted perimeter. Okay, now come to the next, that is about the velocity distribution. It is very important. Next topic is, So what is the velocity distribution? The velocity at a solid boundary must be 0. And in open channel flow, it generally increases with distance from the boundary. Okay, I will show you the figure also. The maximum velocity does not occur at the free surface, but it usually below the free surface at a distance of 0.05 to 0.25 of the depth. The average velocity along a vertical line is sometimes determined by measuring the velocity at 0.6 of the depth. Okay, this value you have to remember. But a more reliable method is to take the average of the velocity at 0.2 and 0.8 of the depth, 0.8 meter of the depth, according to measurement of the US Geological Survey. So you can see here I have shown some figures. So here you can see in this particular figure, velocity increases away from the friction of the banks and bed. In wide channel, W by D, if you take and this ratio is suppose greater than 15, velocity gradient and boundary C are greatest at the bed side. You can see I have shown through arrow. In narrow deep channel, steepest gradient against bank. Okay, hence tendency to bank erosion. So there is chances that bank erosion will be there. Channel shape will determine the velocity distribution. So ultimately what I want to say, your channel shape, okay, is determine ultimately how your water is flowing, means velocity distribution is. Okay. So this is all about velocity distribution in river channel. Now come to the next subtopic, that is the best hydraulic channel cross section. There are so many channel section are there, rectangular section, trapezoidal section, circular section. So we have take this particular topic. So what is that? Some channel cross section are more efficient than others in that they provide more area for a given weighted parameters. From the Manning's formula, it is shown that when the area of cross section is minimum, okay, very important word, is minimum, the weighted parameter is also minimum. And so both lining and excavation approach their minimum value for the same dimension of channel. So the best hydraulic section is the one that has the least weighted parameter or its equivalent, the least area for the type of the section. This is called best hydraulic section. The Manning formula, you know, it is Q is equal to 1 upon A, 1 upon N, A R raised to 2 by 3 into S raised to 1 half, because here we have taken in the form of Q. Okay. So in which Q is the discharge. LQ by T means we had defined here our Q in MLT dimension. Okay, meter cube per second. Meter means L cube, second means time, so L cube by T. A is the cross sectional area, cross sectional flow area. R is nothing but area divided by weighted parameter. Okay, you know very well, A by P. The hydraulic radius. S is the slope of the energy grade line. Small n is the Manning roughness factor. Cm is the, okay, an empirical constant equal to 1.49 in USC unit to 1 in SI unit. So this is just for your understanding purpose. So you can see here, this is the rectangular cross section, this is your depth and this is your width, and this is your trapezoidal cross section. Okay, width is B, depth is Y, and we have taken side slope. Okay, M is to 1. So when Q and S are known, equation 1 can be written. Okay, we have already written the equation. Okay, so this is your equation number 1. So if you want to write, you can write this way: A is equal to C into P raised to 2 by 5. So in which C is known, and this equation shows that P is a minimum when A is minimum. And to find the best hydraulic section for a rectangular channel, I already shown the figure. P is nothing but B plus 2y and area is nothing but B into y. So you just put the value, so you will find this equation: A is equal to P minus 2y in bracket into y, which is nothing but this is C, so C into P raised to 2 by 5. Differentiating with respect to y, you will find this equation. Okay, and setting dp by dy is equal to 0 gives P is equal to 4y, means P is nothing but B plus 2y, so you will get P is equal to 4y, means B is equal to 2y. Therefore the depth is 1/2 the bottom width independent of the size of the rectangular section. Okay, so right now we are just deriving the best hydraulic section for rectangular section. So to find the best hydraulic trapezoidal section, okay, there's the figure number 2. This is the figure number 2. We are derive right now for figure number 1, that is the rectangular cross section. Now we will derive for trapezoidal section same way. So A is equal to by plus my. M you have to take, slope you have to take here. Okay, side slope, and P is equal to B plus 2y under 1 plus m square. And after eliminating B and A in this equation, we will get this equation: A is equal to by plus my square, which is equal to P minus 2y under 1 plus m square. bracket complete into y plus my square. Just put the coefficient, so your equation will be c into p raised to 2 by 5. And by holding m constant, if you take your slope constant, side slope, and by differentiating with respect to y, del p upon del y is set equal to 0. So your equation will be reduced to here, p is equal to 4y under 1 plus m square minus 2my. So equation 5 is differentiated with respect to m, and del p upon del m is set equal to 0. So you will get your final equation this way: 2m upon under 1 plus m square is equal to 1, means m is equal to under 3 by 3. If you solve, you will definitely get this answer. I have just uh, okay uh, deriving very in a very brief. Okay, if you find your book, you will get all the derivation in detail. Okay, and after substituting for m value in equation 4 or 5, you will get p is equal to 2 under 3 into y, b is equal to 2 under 3 upon 3 into y, and a is equal to under 3 into y square. Okay, so by this way we have derived the best hydraulic section for rectangular as well as trapezoidal. There are some more circular section is also there for maximum velocity condition, okay, for maximum discharge condition. So you can find that particular from your book. I am here, my approach is that to give some idea about the basic concept, okay, in open channel flow. Next one is steady uniform flow. As already mentioned, the condition of flow, that is the depth of the flow, average velocity do not change with respect to time and also remain the same at all sections. Very important, all sections along the channel in the case of steady uniform flow. We have discussed steady flow, we have discussed unsteady flow, we have discussed uniform flow, we have discussed non-uniform flow. Now here we have taken the combination of steady and uniform flow. Okay, so what is the meaning of that? Okay, depth of the flow, average velocity do not change with respect to time and also remain the same at all section along the channel in the case of steady uniform flow. Uniform flow is possible in case of prismatic channel, and the actual condition of flow vary with respect to time. Okay, prismatic channel, non-prismatic channel. Prismatic channel, you can take example of river whose cross section is not generally canal is your prismatic channel whose cross section is generally not very, and your river your non-prismatic channel in which your cross section of the channel is generally varying. So the actual condition of flow vary with respect to time. To simplify this condition, steady uniform flow condition are assumed. So in the case of steady uniform flow, it is therefore apparent that the channel bed, water surface line, and energy line shall be parallel to each other. You can see the figure. These all are parallel to each other. Okay, you can see the figure. Now, specific energy and critical depth. In open channel flow, there are so many subtopics. So we are taking one by one each and every topic, and we are discussing in very brief all the topics. So energy per unit weight, that is ES, S for specific, E for energy. Specific energy with elevation datum taken as the bottom channel and is called as the specific energy. And it is plotted vertically above the channel. And this is the equation mathematically if you want to determine ES is equal to Y plus V square by 2G. This is a fundamental equation. A plot of specific energy for a particular case is shown in figure 12.6. I will show you the figure. You can see this is the example of specific energy. You can see this is your specific energy. This is your V square by 2G. Okay, this is your depth. So a plot of specific energy for a particular case is shown in the figure in a rectangular channel in which Q is the discharge per unit width. Okay, so you can write by this way: ES is equal to Y plus Q square upon 2G Y square. And it is of interest to note how the specific energy varies with the depth for a constant discharge. So that is figure number 12.7. You can see specific energy required for flow of a given discharge at various depth. At various depth. This is your various depth. Y, your depth, and this is your specific energy. So for small value of y, the curve goes to infinity along the ES axis. While for the large value of y, the velocity head term is negligible and curve approaches the 45-degree line, means ES is y absolute. So you can see. So here it will make the 45-degree angle. Okay. The value of y for minimum ES is obtained by setting, means if you take the differentiation with respect to dy equal to 0, then from equation 12.5.2 that we have this mentioned here, this, okay, your equation will become to like this: ds upon dy is equal to 0, which is nothing but 1 minus q square upon gy cube, means yc. Yc is equal to q square upon g raised to 1 by 3. Okay, and this is called, Yc is called critical depth. The depth for minimum energy, that is Yc, is called critical depth, and eliminating q square in equation 12.5.2 and 12.5.3 gives that Es is minimum at 3 by 2 Yc. At 3 by 2 means 1.5. 1.5 times of the Yc. Showing that the critical depth is 2/3 of or the specific energy, means eliminating Es in equation 12.51 and 12.54, we get Vc is equal to under Gyc. So you can see ultimately what I want to say, that is the general about the specific energy. So we know what is the specific energy, we know what is the critical depth, and what is the relation between the specific energy and critical depth, that we have mentioned here. Okay, when your specific energy is minimum, okay, so what is the relation between the critical depth and specific energy, that we have mentioned here, we have derived here. Now next one is hydraulic jump. Okay, so what is hydraulic jump? Next topic is hydraulic jump. What is hydraulic jump? If a supercritical flow, we already discussed what is supercritical flow based on the Froude number, what is subcritical flow. So if a supercritical flow suddenly changes to a subcritical flow, a hydraulic jump is said to have occurred. And the change from supercritical to subcritical flow may occur as a result of an obstruction. As a result of an obstruction placed in the passage of the flow, or the slope of the bed provided is not adequate to maintain the supercritical flow. For example, water falling from a spillway. So at a time hydraulic jump will occur. Okay. I will show you the figure. Where is the figure? Okay, 1 minute. I will show you the figure. Okay, figure. Okay, come to here. Okay, this is the figure you can see. Okay, so for subcritical flow, disturbance caused by a change in the bed slope or flow cross section may move upstream and downstream, and result is a smooth adjustment of the flow. However, when the flow is supercritical, disturbances cannot be transmitted upstream, and thus a gradual change is not possible. Okay, so water is flowing from a height, okay, from a spillway to downstream, so there is chance that it will erode the floor of the basin. Okay, that's why we provide, means ultimately it is a because of the, you can say it is from the hydraulic jump. Okay, so the transition from the supercritical to subcritical flow occurs abruptly through the hydraulic jump. You can see here hydraulic jump is formed. Now what are the uses of the hydraulic jump? So these are the uses. Hydraulic jump can and do occur naturally, for example in and after rapids in river, and they are also deliberately created to dissipate the energy after a spillway and to prevent the scouring and to recover the head downstream of an obstruction. Okay, so this is nothing but ultimately what is the meaning of the hydraulic jump. So in this particular session we have discussed very common basic concept. Okay, what is open channel flow, what are the example of open channel flow. Okay, then some of the basic concept, conservation of loss. Okay, classification of open channel flow, steady flow, unsteady flow, uniform flow, non-uniform flow, laminar flow, turbulent flow, based on the Froude number, subcritical flow, supercritical flow, critical flow. Okay, then we have discussed velocity distribution in open channel flow, then some terminology which is very important in the open channel flow. Okay, parameters. Then we have discussed hydraulic jumps, then we have discussed specific energy. So these all concepts are very important. And one more thing, that though I have taken today this lecture and I told you this is the meaning of this all the terminology, but as when we go further, okay, we have to get some basic idea of the fluid mechanics terms, because in fluid mechanics there are a lot of derivations are there, a lot of assumptions we are taking when we have to derive any theory. So if you have some basic of fluid mechanics, then we can understand easily this all the chapters. If you directly go to the derivation and any theory, you can't understand properly. So today my aim is that in introduction of about open channel flow, that I have covered some basic portion in this particular session. Okay, So here I am ending my this particular session. Now I am just open my questioning session. So if you have any query related to this particular session, okay, you can ask. Today we have completed our session, okay, for 11:43. Still we have 15 minutes. So if you have any query, you can ask me. Tomorrow we will again discuss one more topic, that is the introduction about centrifugal pump, and that is again very important, not only for fourth semester student, also for sixth semester student also, and also for mechanical student also. Okay, centrifugal pump. So again in that lecture we will cover some basic parameters. So please join tomorrow also. And tomorrow our time is at 10:30. Okay, we will start half an hour early, 10:30 to 11:30. So I am very thankful to you that you attended in so many numbers. Okay, so dear student, if you have any query, you can just ask me. Otherwise, you can personally do the email on my email id. I already mentioned my email id in previous lecture. Again I'm mentioning: kbpatel 5 times 9 99999 at the rate gmail.com. You just put your query, okay, and I will try my try level best to solve your query. Because in a 1 hour lecture it is impossible to cover each and every topic, you know very well. That is our limitation. So if you have any problem related to fluid mechanics subject in any topic, okay, you just put a mail, and we will definitely come up that particular whatever question you have. We will definitely come with the solution. So if you don't have any query, so we will just closing our this session. Okay, I am very thankful to all the participant that they have attended this webinar. Okay, thank you so much.